there any questions over the previous homework assignment? Any questions over the assignment yesterday? Okay. Also, because obviously y'all know there's a lot of people that are out for today for weightlifting or show, would be nice, and if you haven't got all the assignments turned in from the last chapter, this is the last time I'll extend it to Monday. If you can get it first thing Monday, I'll take them. After that, there's going to be zeros, and that's probably going to hurt some of y'all's grades. So make sure to get those turned in and work on them. If you do have questions over the weekend, please reach out, email me. I'll respond pretty quickly. Just make sure to send a picture of the question that you have. That way I'm not going to have to try to pull it back up and then see what it is. Answer the question a little bit quicker. All right. So what we're looking at today is dealing with more of our properties with our rational exponents, these rational roots. And the first one's talking about our a to the m over n. A to the m over n can be rewritten as a to the 1 over n times m, which can be rewritten as the nth root of a to the m. Or vice versa, or conversely, we can also talk about the negative exponent, which is going to be 1 over a to the m over n. Because whenever we have a negative exponent, we can move it from the numerator to the denominator or denominator to the numerator to make the exponent positive. And that's all we did. We moved it down so that the exponent went from being negative to positive. And then it's the exact same property. That we can have a to the 1 over n to the m, which is saying that we just have 1 over the nth root of a to the m. And we do this so that we can simplify the expression a little bit easier, especially if it is simplifiable. We want to be able to manipulate it to get to the answer. So let's look at some examples of how this works. So our first one here is 16 to the 3 halves. Well, utilizing this property, what we can say is that we can rewrite 16 to the 3 halves. Calligraphy pen out. Is we can rewrite it as 16 to the 1/2 to the 3rd, because powers of powers multiply, which means we can also break them back apart in this way here. Because 3 times 1/2 is the same as 3 halves. Well, now we can rewrite 16 to the 1/2 as a radical. And the number that goes in our index, or the number in the little v of our radical, is the denominator of the fractional exponent, which here is 2. But we don't necessarily have to write it because it's understood whenever we have a radical without a number, the index is 2. 16 goes inside. And the numerator of that rational exponent would actually go in with the 16, but here it's just 1. Now the question is, can we take the square root of 16? Well, yes. The square root of 16 is 4, and we have 4 to the 3rd. And 4 to the 3rd power is 64. And again, so breaking these apart like this is helpful in trying to figure out what we need to do to it. And especially simplifying these expressions in a way that makes it easier to work with. And that's really the key behind all of this, is rewriting it in such a way that we can simplify it in an easier method. So 32 to the negative 3/5. We're going to work with this here and simplifying it. Now, because the exponent's negative, we need to move it from the numerator to the denominator to make it positive. So here, we're going to have 1 over 32 to the 3/5. this is really telling us that we have 32 to the 1/5 to the third. Now we need to see if we can find the 5th root of 32. Because really that's what we're saying here, is that this is the same as 1 over the 5th root of 32 to the third. Because since the numerator of our rational exponent is 1, we really have 31 to the first. Since the 5's in the denominator, it would become our index, telling us we're taking the 5th root of 32. And there's different ways that we can go about finding it. One is a factor tree, breaking it up into the prime numbers. Times 4. And we actually get to 5 times. Or the calculator would actually find this one and tell us that the 5th root of 32 is 2. Which leaves us with taking 2 to the third, which would be 8. So it tells us that 32 to the negative 3/5 is 1/8. Questions on this here? And again, we're starting off using these numbers here because they're easier to work with and help us better understand these. Because once we start dealing with variables and things that are not just going to simplify out or be a nice number that the calculator can give us, we have a better understanding of how this works. That way we can still utilize it even though it's in a different form. Any other questions on this here? All right. So really we can break this down to see how we can rewrite it so it's easier to work with, yes? Now 64, we're going to be taking the what root of it? The third, yes? Because that's the denominator. So if we wanted to, we could rewrite this as 64 to the 1/3 to the 4th. Which actually tells me that I have the cubed root of.
Riley Shelley, go to the library. Riley Shelley, go to the library.
Cubed root, because since the 1 is in the numerator for our exponent of 1/3, the 1 would go with the 64, just telling us it's 64. The 3 would be our index, telling us that we're taking the cubed root of 64. And the cubed root of 64 is, well, 4. Because 4 times itself 3 times gives us 64. And last but not least, we need to take 4 to the 4th power, which would be 256. Any questions on this so far? I mean, there's different ways we could go about this. So if we notice that 64 is 4 to the third, we could rewrite it in this way. Because 64 is 4 to the third, we can break it down. And powers of powers do multiply together. So we can say 3 times our 4/3 would be 12 thirds, which would be 4 to the 4th, which is our 256. So there's different ways we can get to the answer. It's figuring out which way makes sense to us and utilizing it. Now, if we look at this next one here, we do have the negative 5/4. So what can we do first? make it into the denominator. So we have 1 over 16 to the 5/4. And what can we do next? Mm-hmm. 16 to the 1/4 to the 5th. Now at this point here, we're finding the 4th root of 16. Really, that's what 16 to the 1/4 is, yes? And what is 16 to the 1/4? I think y'all found it to be 2, yes? Because 2 times 2 is 4, times 2 is 8, times 2 is 16. Because we could have written in the step that we take the 4th root. We could have gone down here and said 1 over the 4th root of 16 to the 5th. Well, we would have gotten right back there. Now, the last thing we need to do is find out what 2 to the 5th is. Well, 2 to the 4th we said is what? Multiply 16 by 2 and we get, that's 1/32. Well, I could have, instead of moving it from the numerator to denominator first, we could have done that last. Because I could have kept that negative exponent all the way through to the end and then dropped it down. Because there's many different ways to go about this. It's figuring out which way we find, or you find, the best that makes sense and utilizing it. Because all these properties, we're just manipulating them to get the numbers to simplify. And these are your all's favorites. Because what are our directions for these here? Evaluate using a calculator. Round your answer to the nearest 2 decimal places. Well, our first one's 9 to the 1/5. Figure that out. We don't need that. 9 to the 1 over 5. 1.55. And that's it. Well, the second one is 12 to the 3/8. And again, we just need to plug this in and we would get our answer. And 12 to the 3/8 would be 2.54, I believe, yes? And the last one would be what? 0.30. Yeah, we'll still need the 0 because that's where we rounded to. Any other questions on these here? We kind of like these here, yes? All right. We could do 3 more, but I don't think that's helping reiterate your ability to type it into the calculator. This is the last thing we're going to look at. To solve an equation of the form u to the n equals d, where u is an algebraic expression, take the nth root of each side. We've actually done this before. But we called it the square root method. And we called it the square root method because our exponent was a 2. This is the exact same thing. It's the exact same steps, except we're not guaranteed that we're going to take the square root. We could take the square root still, but it's not guaranteed. but the steps for solving it are the exact same. And whenever we use this, either we have a variable by itself, we don't have multiple variables, we only have one, or the variable's in a set of parentheses to an exponent. Here, we only have one variable and it's x to the fifth. So we want to get it by itself. So the first thing we would want to do, divide both sides by 4. And when we divide both sides by 4, 4x to the fifth divided by 4 is going to be x to the fifth is equal to 32. Now in the square root method, we would square root both sides to get our answer. But here, can we take the square root of both sides? No, because what is our exponent? So we would need to take the fifth root of both sides. And the fifth root of x to the fifth simplify out giving us x. Because realistically, what we're doing is we're saying that we have x to the fifth to the 1/5, which when they multiply together, we get x to the 5/5, which is just x to the first, which we just say is x. But we don't have to do that every single time because we know that the fifth root of x to the fifth would become just x. Now we need to find out what the fifth root of 32 is, which is 2. Now, did we take an even root or an odd root? An odd root, yes? And like we saw yesterday, if we take the odd root of a negative number, we have one real solution. If we take the odd root of 0, we have one real solution. And if we take the odd root of a positive number, we have one real solution. So that is the answer. Really, the ones that get tricky are our even roots, because we can't take the even root of a negative number and get real solutions. The even root of 0 is just 0. And the even root of a positive number gives us our plus or minus. Here's our other type. Is this one here, we have a set of parentheses. So there's two different ways we can go about it. One is easier than the other. Because the harder route would be to say, okay, so we have x minus 3 to the fourth. Well, I can multiply x minus 3 by itself 4 times and get that fourth degree polynomial function, set it equal to 0, and solve. But we'd actually still get the same answer. So the easier route, and the route we're going to take, is since x minus 3 is the only place where there's an x. Yes? Doesn't show up anywhere else. We don't have to do that multiplication step. The only time that we would really have to do that is if there's a variable somewhere else outside of those parentheses. Then we've got to get the like terms together and solve that way. But here, all the variables are stuck inside that parentheses. And really what we're looking at is saying that term to the fourth is equal to 21. That's really kind of what we're treating it like. Because what we can say is that I can take not the square root of both sides, but the fourth root of both sides. Because as we know, these will cancel out, simplify out, leaving us with x minus 3 is equal to fourth root of 21. Now, I was kind of quick in just writing the fourth root of 21, yes? Well, fourth root, we're looking for a number that multiplied by itself 4 times gives us 21, yes? Well, 2 is 16. 3 is 81. 21 it doesn't have a chance to be a whole number. So we can leave it as the 4th root of 21, yes? Okay. Well, is that index even or odd? Is that root even? It's even, yes? Okay, that's the tricky one. Is the number inside negative? No, okay, so that means that this does actually have a real root. Well, it's not 0, but it is positive, yes? So how many roots will we have? 2. We need the plus or minus. We need the plus or minus. Okay, is x by itself? No, okay, so we got to do one more step. We need to add 3 to both sides. There's nothing wrong with putting the 3 second, but it is standard form to put the 3 in front of that plus or minus. Well, any questions on this here? Now, we've already said that the 4th root of 21 isn't a nice number, correct? It's an ugly decimal. So as it stands right now, could I add 3 in the 4th root of 21? Or could I subtract those? Well, we could. I just have to change the 4th root of 21 into a decimal, yes? Let's look back at the instructions. Find the real solutions. Did it tell me to approximate or round to the nearest tenth or do anything like that? Well, no. Okay. There's your answer. You know that you'll need to simplify it if it says to find the approximate solution, round to the nearest whole number, round to the 10th. When it starts talking about rounding, we have to simplify this. We have to take 3 plus the 4th root of 21 and 3 minus the 4th root of 21 to see what we get. Otherwise, we can just leave it as this here. Questions on this here? All right. Find the real solutions of 5 to the 3rd is equal to 320. Okay, what can we do first? Divide both sides by 5. And if this was me, especially on the ACT, I wouldn't even rewrite the thing. I'd just start working on it from where it's at. Because 5x to the 3rd divided by 5 is x to the 3rd is equal to well, what are we going to need to do next? Cubed root it. What's the cubed root of 64? 4, okay? And again, if this was the ACT, I would have looked at the answer, found 4, and moved on. But here, it's definitely good to write out our steps. Because we can cube root both sides, which tells me x is equal to 4, because the cubed root of 64 would be 4. Now, since the root is odd, how many roots would we have, real solutions? 1. And that'd be it. Any other questions on this here? I want to, do we feel comfortable with ones like this here, where we don't have parentheses? Okay. No. I want to look at this one. Because the others aren't really any different, even with a fraction in front, where you can just divide by 1/2 or multiply both sides by 2, the reciprocal of that fraction. Now this one here, we do have a set of parentheses where the variable is. We need to get the parentheses by itself. Well, luckily they are, because there's nothing being multiplied in front, and there's nothing being added or subtracted to it. So the first thing we can do is really take the 4th root of both sides. Now the fourth root of x plus 5 to the fourth, well, these would cancel, telling us x plus 5 is equal to 2. Because the fourth root of 16 is 2. 2 to the fourth is 16. But what root did we take? 4, yes? 4 is even or odd? So even root with a positive number means this is positive or negative. Because realistically, if we're taking the fourth root, that means we're dealing with an even function. And as if we remember back to our higher degree polynomials, they look like a U. They'll both end up going either both up or both down. So that means it's going to cross the x-axis at least twice, or none at all if it doesn't have real solutions. But x is not by itself, so we have to subtract 5 from both sides. Which would really tell us that x is equal to negative 5 plus or minus 2. Now in the last one we did where we had an even root with plus or minus, we kind of circled and said we're done, yes? But this one's different. Because this time we have 2, don't we? Because in the last one, the fourth root of 21 wasn't a nice number. And we couldn't really add or subtract without changing it to a decimal and approximating and rounding. Here, can I do negative 5 plus 2? Can I subtract them? Yes. If we can actually add and subtract, we're going to need to add them, and we're going to need to subtract them. Well, negative 5 plus 2 is negative 3. And negative 5 minus 2 is? So the answers are negative 3 and negative 7. And that's it. Any other questions on this here? Any other ones that we want to look at? Oh, yeah, and this says round, but we good with these here. And that is it for our lesson today. So your homework is on page 245, 27 through 32, and 36 through 41. So you do have some time. You have about 15 minutes to actually get started on this. So you probably could get a good chunk of this done in here.